Welcome to Keentel Engineering. In May 2026, NERC finalized a 47-page reliability guideline that rewrites the relationship between large industrial loads and the bulk power system. If you design, build, own, or operate a data center, an AI training campus, a crypto mining facility, or a hydrogen electrolyzer plant, this guideline now applies to you, mapping specific obligations across 12 entity types. The core message is simple. Large loads are no longer passive consumers. 4 failure modes drove this shift. Customer-initiated load reduction, hundreds of megawatts of voltage-sensitive load disconnecting simultaneously during a remote transmission fault, even when service was never actually lost. Forced oscillations, where cyclical AI training and arc furnace loads interact with natural electromechanical modes between 0.1 and 2 Hz. Resource adequacy mismatches, where demand is outpacing transmission and generation build-out. And cascading over frequency, where a load reduction event creates a sudden generation surplus that trips generators offline in turn. NERC organized its recommendations into 9 chapters, each mapped to specific entities: data collection and modeling, covering dynamic models and as-built equipment states; interconnection studies, covering steady-state, dynamic, and short-circuit analysis with new restudy triggers; long-term planning, covering resource adequacy and fuel dependency risk; operations and balancing, covering forecasting and 24/7 contacts; stability, covering ride-through and oscillation attenuation; power quality, covering harmonics to the 100th order under IEEE 519; physical and cybersecurity, aligned to the CIP framework; resilience and load shedding, covering partial segmentation; and a closing chapter, mapping responsibility across all 12 entity types. A handful of numbers now define compliance. 60.5 Hz is the continuous overfrequency limit in the Eastern Interconnection, 60.6 Hz everywhere else, and ERCOT sets a 60.4 Hz transient limit. 0.1 to 2 Hz is the electromechanical oscillation range under scrutiny. A short-circuit ratio of 2 or below triggers weak grid electromagnetic transient screening, and harmonics now have to be characterized out to the 100th order. So what actually changes for your project? More data gets requested earlier. Dynamic models and ride-through curves are now expected during interconnection evaluation. New restudy triggers mean a changed compute mix or a revised build-out schedule can force a full restudy. Operational duties don't end at energization, and commissioning repeats as each new tier comes online. Keentel helps close that gap, building dynamic modeling packages that satisfy MOD-032 and FAC-002, running voltage ride-through compliance studies, designing harmonic mitigation to the 100th order, supporting commissioning with fault and disturbance recording, and building telemetry and 24/7 contact frameworks. Our first case study, a 380-megawatt AI training campus 14 miles from the nearest 500 kilovolt substation, sitting on a weak grid with a short-circuit ratio below 2.5 normally and below 2 under contingency. GPU cycling produced oscillations landing right inside a local generator mode, and the facility's backup power logic risked a 220-megawatt step disconnection during a normally cleared fault. We built site-specific electromagnetic transient models with the equipment vendors, added rack-level storage and workload smoothing, and revised the ride-through profile. The agreement finalized 5 months late, but avoided the 18 to 24-month delays competing weak grid sites saw, and the facility's measured data validated within 6% of simulation. Our second case study, a 220-megawatt facility approved as a data center in the ERCOT footprint. 18 months into construction, with the substation built and the transformer energized, the developer pivoted to an ASIC crypto mining facility, a textbook-qualified change. We assembled harmonic spectra and ride-through documentation in 3 weeks, benchmarked the dynamic model against an electromagnetic transient model, supported the load reduction contingency analysis, and designed a passive filter bank for the affected harmonic orders. The restudy closed in 11 weeks against the transmission planner's 4 to 6 month estimate. The facility's worst-case load reduction contribution came in at 75 megawatts within tolerance, and the financing milestone held, with energization just 6 weeks behind the original target. Our third case study, 3 hydrogen electrolyzer facilities totaling 355 megawatts, or 38% of the area's existing peak load. The existing under-frequency load shedding program, sized for the old peak, would have dropped to just 18% of the new peak, below the required design basis, and ramp rates up to 70 megawatts per minute strained the Balancing Authority's regulation reserves. We redesigned the load shedding allocation across 3 stages, segmented each facility into 4 controllable blocks, and built detailed ramp profiles for reserve sizing. All 3 facilities received signed interconnection agreements on schedule, and partial shed events performed exactly as designed through the first 18 months with no full facility outages. Who does this apply to? 13 entity types. If you design, build, own, or operate a large industrial load, it applies. Is it mandatory? No, voluntary today, but built to bridge into binding reliability standards already in development. What counts as a large load? No fixed megawatt threshold. Any facility whose demand or profile could pose reliability risk. How is a large load entity different from a registered entity? Not yet NERC registered, but encouraged to act as if it were. What's the difference between as designed, as built, and as left? 3 model states tracked and updated whenever a qualified change occurs. When do I need an electromagnetic transient model? When short circuit ratio is 2 or below, large power electronics are present or load fluctuates rapidly. What is a qualified change? A demand or model change above a set threshold that triggers mandatory restudy. What monitoring is required? Fault, disturbance, and sequence of events recording at the transformer's high side. Do I need a 24/7 operational contact? Yes, load reduction events develop in seconds, leaving no time without one. What is customer-initiated load reduction? Voltage-sensitive equipment disconnecting during a remote fault, hundreds of megawatts can vanish at once. What is the most severe load contingency? The load side equivalent of a generator's worst-case contingency used for reserve planning. What ride-through must I support? Low and high voltage curves, rate of change of frequency, phase jump tolerance, and over-frequency limits to 60.6 Hz. Should AI training operators worry about oscillations? Yes, cyclical GPU loads have produced real documented events already. What harmonic limits apply? IEEE 519, characterized to the 100th order, with restudy triggered by late-stage increases. Could my facility join load shedding? Yes. Once it rivals a feeder, partial segmentation is now a baseline expectation. Where do I start if I'm already interconnecting? Appendix A's responsibility matrix, find your lead items, then build a gap closure plan. In May 2026, NERC quietly rewrote the rules for large loads. Data centers, AI training campuses, crypto mines, and hydrogen electrolyzers are no longer passive consumers. They're active grid participants. The guideline demands dynamic modeling, ride-through coordination, harmonic analysis, and real-time operational contacts starting at interconnection, not commissioning. It's voluntary today. The reliability standards behind it won't be. At Keentel Engineering, we've already guided projects across ERCOT, PJM, and MISO through this exact shift. Visit KeentelEngineering.com.